Alright, so today we're going to finish up 7.4b that we left off on yesterday. So we're going to do trig substitution continued. So we're looking at example 4 in your textbook, which is on page 502. So if you want to look at page 502 of your textbook, that's the example we're looking at. So here we actually have limits on our integral. So we're going to learn how to convert them because we can't use the same limits for x's that we do for trigonometric functions. We have to actually convert them into the appropriate limits for the trigonometric functions. So here is how we do that. First of all, let's look at the square root that we have. So I'm looking at the square root of x squared minus 3. So I notice that u is going to be x and a is going to be the square root of 3. So if I set out my little triangle over here, I have a minus, so I know that my square root of x squared minus 3 is going to be one of my legs. That makes x the hypotenuse, and the square root of 3, it makes that the other leg. If you look back at yesterday's notes, the trigonometric substitution, this is the third example. So integrals involving the square root of a squared minus u squared minus a squared. So we actually have that variable term first in our subtraction underneath the square root. So when that happens, we have that x is going to equal, I don't want to use the square root of x squared minus 3 because that'll make it more complicated. So I have the adjacent side and the hypotenuse, and I want that x to be on top. So I want to have hypotenuse over adjacent, which is the reciprocal of cosine. So that would be secant. So x is going to equal the secant of theta. Don't forget to include when you multiply over, because it was x divided by the square root of 3 originally, and I'm going to multiply that over to this side. So I need to include the multiplication of the square root of 3 over here. If I take the derivative of that, I get that dx equals the square root of 3. Derivative of secant of theta is secant theta tangent theta. D theta. And then what else do I need to know? I also need to know what the square root of x squared minus 3 is. So if I use that and the square root of 3, I have opposite over adjacent, which is tangent. So I'm going to have that be the square root of 3 times tangent of theta. Alright, so I can plug those things into my integral. The only thing is that now I have to worry about those two limits that I have on there. So I'm going to look at when x equals the square root of 3, because this is in terms of x's up here. So when x equals the square root of 3 and when x equals 2, let's see what theta would equal. So if x equals the square root of 3, and I know that x is equal to secant theta times the square root of 3. If I want to solve for theta in this, I can divide both sides by the square root of 3. So I get that 1 equals secant theta. Secant theta is the same thing as 1 over cosine, so that's 1 over cosine of theta. If I solve for cosine by itself, I get cosine of theta equals 1 over 1, which is just 1. And I'm trying to ask myself, where does cosine of theta equal 1, and the answer to that is that cosine of theta equals 1 when theta equals 0 degrees, or 0 radians. So I know that my lower limit is going to be 0. Sorry, you can barely see that down there, but it says theta equals 0. Now I need to find my upper limit, so I'm going to go back and erase this. So let's see when x equals 2, that equals secant of theta root 3. If I divide both sides by root 3, I get that secant of theta equals 2 divided by the square root of 3. Again, I know that the reciprocal of secant is 1 over cosine, or that secant equals 1 over cosine. So if I take the reciprocal of that, that would be that cosine of theta equals the reciprocal of this side, which is root 3 over 2. And if you go back and look at the unit circle, cosine of theta equals root 3 over 2 when theta equals pi over 6. So that's my upper limit, is pi over 6. So my lower limit is 0 degrees, my upper limit is pi over 6, or 0 radians, my upper limit is pi over 6. So now when I plug everything back into my integral, I have the integral from 0 to pi over 6. The square root of x squared minus 3 equals the square root of 3 tangent theta. Dx equals the square root of 3 times secant theta tangent theta d theta. And on the bottom I have that x, and x equals secant theta times the square root of 3. So if I'm looking for things that cancel, I have the square root of 3, the square root of 3, secant theta, secant theta. So I'm left with the integral from 0 to pi over 6 of root 3 tangent squared theta d theta. So I can pull out that root 3 and the integral of tangent squared theta. There is no easy integral. So let me erase some of this stuff over here so we have room. Alright, so I have the square root of 3 times the integral from 0 to pi over 6. Like I just said, there's no easy integral for tangent squared theta, so I'm going to actually use one of my trig identities to say that tangent squared theta is the same thing as secant squared theta minus 1. And now I can split up the integral into two separate pieces, so I have the square root of 3 equals the integral from 0 to pi over 6 of this integral of secant squared theta d theta minus the integral from 0 to pi over 6 of d theta, 1 d theta I should say. So that's root 3, and then the integral of secant squared theta is tangent theta. The integral of d theta is theta, and that's from 0 to pi over 6. If you plug in pi over 6 to this, and if you plug in 0 and you subtract those, you get root 3 over 3 minus pi over 6, and then minus 0, because when you plug in 0 to both tangent theta and theta, it equals 0 in both of those. Check just to make sure that you're understanding all of this, and then keep writing. If you multiply over here, I get root 3 times root 3 is 3, divided by 3 is 1, minus the square root of 3 times pi divided by 6. And if you put that in a calculator, that's about equal to 0.0931. So if you look back at the original example, it was asking you to integrate that using those conversions of the limits, So that's the main thing that we're practicing here is a little bit of what we did yesterday, but also figuring out how to find new limits for our integral. So that's how you do that, and we got an answer for the definite integral for this problem. All right, the next problem and the last problem we're actually going to look at is on page 504 in your book. Example number 5, which is actually an application of this process. So if you actually want to go back to your notes paper from yesterday, you can do that. And we can just write it here under applications. So there's this section here on yesterday's notes for applications. You guys can just write this down for applications. That's fine, since you have so much blank space there. So for example 5, let's write that down. Example 5. So example 5 says find the arc length of this graph. So if you look at page 504 in your textbook, you'll see that graph. So it's find arc length of f of x equals 1/2 x squared from x equals 0 to x equals 1. And there's that picture of it in your book right there that you guys can see. Now you may or may not remember back to section 6.4, so if you don't remember, you can go back and look at section 6.4 in your book. But section 6.4 is talking about arc length, and it gives a formula for arc length. So if you don't recall it off the top of your head, you can write it down. They use S to stand for arc length, and they say that the integral from a to b, whatever length you're trying to take, is the square root of 1 plus the derivative of f quantity squared. So if we plug in what we know that s equals, the limits of integration are going to be from 0 to 1 times the square root of 1 plus the derivative of f is 2 times 1/2 x, or in other words just x, so that's x quantity squared dx, Now again, this looks a lot like what we've been doing recently. So if I look at my little triangle, I have that my hypotenuse is 1 plus x squared. That means this is x and this is 1. So I know that x equals, that's going to be opposite over opposite over adjacent, so that's tangent. So that's tangent of theta. That means that dx equals secant squared theta, d theta. And last but not least, the square root of 1 plus x squared equals secant theta, because I have hypotenuse over adjacent, so that's secant theta. So I can plug everything in. I need to find my new limits of integration. So when x equals 0, what does theta equal? Well, when x equals 0, I'm looking here. If I plug in 0 for x, I get 0 equals tangent theta. And tangent of theta equals 0 when theta equals 0. So that means this has to be 0. And for my upper limit of integration, when x equals 1, if I plug in 1 for x, I get tangent of theta equals 1. And that happens when theta equals pi over 4. So if I plug in everything, I get the integral of 0 to pi over 4, from 0 to pi over 4, of secant theta times secant squared theta d theta, which, if I erase some of this stuff up here, becomes the integral of 0 to pi over 4 of secant cubed theta d theta. And you have a couple options. You could go back to the previous sections and look at how to do this using what we've learned in the previous sections. Or if you look at your notes from yesterday, we wrote down those 3 special integration formulas when a is greater than 0. And this one falls under, if you look back, it was the square root of 1 plus x squared, which actually falls under the last integration formula. So, the special integration formula. So you can just use that if you'd like, but it's good to know how to get there, so maybe you want to practice doing it the other way in previous sections, how we did it. I'm just going to use our little shortcut though. So I know that using our third special integration formula, it gives me that the integral of secant cubed theta is 1/2 times secant theta tangent theta plus ln of secant theta plus tangent theta from 0 to pi over 4. Now I want you to go back and I want you to check to make sure that you understand how we got there. If not, make sure you come ask me about that. And if we simplify and we plug everything in, so we plug in the 0 to pi over 4, we get that 1/2 times the square root of 2 plus ln of the square root of 2 plus 1, which, if you put that in a calculator, is about equal to 1.148. So that is the length of the arc of that curve from 0 to 1. Again, make sure that you understand where we got this piece from. All right, that's really crucial that you would be able to do that on your own and get that piece on your own, either by memorizing the special integration formula or by going back to the previous section and understanding how we get this from what we learned in the previous sections. All right, that's it for today.